Good evening, everyone. This presentation is a high level of review of different LLM evaluation methods. And I did a lot of LLM evaluation in my company in Zilliz. I recently left them. I also consult and help a lot of companies who are developing different use cases using LLM. And I see evaluation is one of the areas which I believe mostly underappreciated, and I will explain why through a presentation. And I also have GitHub small repository, small collection of links to the articles I consider important. So if you want, you can visit there. And I intentionally don't keep only like many people when they talk about evaluations, they talk only about benchmark articles. I intentionally also find and share their all good articles such that they develop a new LLM, but inside there is a good section about how they did evaluation. So they are also there. And why I believe evaluation is so important. I started in early Google in 2006, my career after my PhD. And as you remember, it was very hot competition between Google, Yahoo, Microsoft. And I believe one of the reasons, there are many others, but one of the reasons why Google became successful is evaluation was really good, and it was driving whole development to the better. I will talk a little bit in more details of how is it relevant to LLM. And there is a good quote from Greg Brockman, who is president of OpenAI. Evals are surprisingly often all what you need. And purpose of this presentation is more like not to go deeply into one particular metrics, but talk about good practices such that as you develop your systems, and it can be either search systems based, question answering, or copilots, what's the good practices such that you can use for your system evaluation. And just a little bit about myself. So I started in Google in 2006. I was one of core contributor to Google Core Search, one of core components. Then I built Apple Map Search. I significantly changed Apple App Store and iTunes. I was leading search in Walmart, eBay, recently Zillow. And of course, search is very heavily based on NLP first, but also large language, of course, language models before large language models. It was quite heavily used since early 2000s. And of course, as you know, all recent migration to BERT first and then to large language models recently. So there is kind of a lot of use of them in search. And again, my talk will be more focused there is a lot of evaluation certainly on first pre-training stage, but very few companies will be focused on that. Most companies will be doing for different types of fine-tuning, RLHF, and so on, to tune LLMs to their particular use cases and also building systems. And my intentionally focus is not on the first benchmarking and evaluation, but more on the second, because more companies feel business and it's more aligned to their businesses. So how is it different comparing to classical machine learning, right? Typically classical, it's not always true, but typically classical machine learning, you have a model which is focused on one task and you have one metrics. You want to predict the best price of the house, or you want to predict what will be future average price for this item in 1 week, whatever, right? You have very clear task, you have one metrics, and it's hard, but relatively simple. With large language models, it's the foundational models, right? There are many other different types of foundation models, but what's typical, one model is used for many different tasks, and there are many different metrics. So as you develop LLM inside your organization, then it's not you will use it for one particular use case. There will be many different use cases, tasks used by different teams, and of course, different metrics and the question how to evaluate and deploy it correctly. And I know some organizations, I recently talked to one, they have 600 LLMs inside the organization, and it's not jokes, they truly use this, right? It's one big organization. So there are some companies kind of looking, let's fine-tune separate LLM for each use case. I believe this will not be viable in long term. Most probably there will be several key LLMs for different kind of covering different areas. Certainly not one, but not small. And another complexity of LLM evaluation, LLMs are used for very different tasks, right? Not just for different NLP tasks. I'm talking about LLMs. Very different. It's kind of generic area, but even in first different tasks, but also typically inside company LLMs will be used for many different semantic areas. Is this kind of today was this model released and they compare themselves to ChatGPT. I'm just they evaluate by very different semantic areas like humanities, writing, reasoning, mathematical tasks. But even inside company, the same model will be used for financial department, for search, for multiple different, right? Depends, of course. There are different cases, but it's important that LLM does not show a performance very different in different areas, and it's important to take in evaluation. And it's like this previous slide is not just academic. it's very practical, such that inside now enterprise use cases, you use LLM for very different tasks, and you have to evaluate by all of them. Another, why it's hard to evaluate LLM, there are many different functional properties, like first they contain knowledge, right? Then they do reasoning. There are multiple different, which makes evaluation hard. You have to evaluate these different tasks, and there are very different evaluation sets. Also, frequently, like comparing to, like if your model predicts price, frequently model is not directly exposed to customers. Now LLMs frequently directly exposed to customers. So if you have toxicity, any other undesirable output, it will go directly to customers. So risk function is very high. And it's very important to prevent this. That's why LLM evaluation is so complicated. A little bit about LLM evaluation process, and then I will talk about particular methods, right? So LLM evaluation naturally hard. There are multiple different, and here I'm giving examples, like what are good methods, like there are reasoning tasks, there are multi-turn tasks, right? There are instruction following. They are very different in their nature, task, what you expect LLM to solve, and of course they require very different evaluation methods, how to evaluate those tasks. And like when you develop this in your company, it requires not just to use some benchmarks available online, but to develop those cases for your LLMs. Why do you evaluate LLMs? There are different things, and what from my practice also, how do you evaluate for them is quite differently. First, when you want to launch a new product, right? So you want to have high-level evaluation. Is this LLM currently good to launch something or not yet, right? So how to evaluate quality of item, is it of output, is it good enough to provide minimum level of customer experience? Of course, validation of model changes. You improve LLM step by step, right? But another very important, I believe, role of evaluation, it's like, you have test-driven software development, the same in machine learning. There are multiple how people do, but like evaluation-driven model development, that you create evaluation set and then you continuously improve models to them, right? And whole evaluation set drives your whole system development, and that's why evaluation is so important. There is very important parts, like typically if you consider academic benchmarks, there are many of them, they focus on average case behavior, while when you design something for business or for customers, frequently you need to understand worst case behavior or best case behavior. Like for example, if you expect such model can be produced toxic or racial or some other like answers, right? You really care about worst case behavior, rather it will happen just one time per X cases. So analysis for worst case behavior is quite important, frequently not taking academic benchmarks, really important to do in industrial benchmarking. Risk estimates, like not just output right, not correct, like classical text classification, but also what risks, right? And again, semantic coverage, all this need to be part of evaluation process. Another what I found is important, evaluation process should be very continuous, very, how to say, continuous, right? Because multiple researchers will work on LLM evaluation, and it means multiple different models should be continuously tested, developed, because like velocity of science production is also very much based how frequently you do experiments, right? You have certain probabilities such that each experiment will succeed, so you need to allow your scientists to have a very frequent opportunity to make fast experimentation. And so like kind of high level requirements to evaluation process must be fast and cheap, such that you can do a lot of experimentation per every scientist. It should not be like in some organization becomes true bottlenecks, they like because scientists cannot do as many experiments because it's expensive, either by money wise or computational power is not available, right? You have to queue many evaluation processes to wait until previous is finished, cheap and fast to get results of your model iteration. Another important evaluation metric should be correlated with customer and business metrics. And of course, like typical NLP metrics are designed by internal NLP principles, are not necessarily reflecting your customer experience. Designing evaluation metrics which will be correlated with customer experience is important one. And then of course, also evaluation must cover different aspects of use of LLM, both by task, by semantic category, by NLP metrics. So there are not just one benchmark, but typically to represent what your NLP case needs, there will be many, many different benchmarks, and I will give examples after. And another really important, what I see kind of minimal requirements, bias-free evaluation. And like recently I talked to one company that they had this case, they use human raters to evaluate LLM output. And what they discovered, Customers, like people, sorry, not customers, raters prefer long results because it seems more natural. But actually, customers prefer much shorter results, right? So raters have a bias, which is very longer results comparing to customers. And it can happen, there are many different biases. It can happen in every evaluation, such that you give high score to something you believe, but it's not really corresponds how people who use your system. So bias-free representation, right? So like your bench, like data sets driving benchmarks must represent distribution of customers is important. Like, for example, if it's like search system for a shopping site, they must represent distribution of queries and so on. Atomic measurement should measure customer experience, what I call alignment. And another important, systems should be efficient. Like if you do experimentation, it should not produce any production damage, like a system high latency or something. If you measure production traffic, or like, and generally, system should be efficient and fast. And again, another important part is like for any evaluation statistics. Like, for example, like there are several arenas that report your results. What's the statistical confidence? And they started recently reporting this, but like for any evaluation, statistical confidence is really important part to understand you have this set of scores. How true are they? And we will discuss several evaluation methods, again, more like high level to give examples what's good, such that for each particular case, you have like this orientation, this landscape. There are like, I think like 300 papers in LLM evaluation, and most of them quite high quality and relevant. So here I will give some high level review of LLM evaluation landscape. So typically when we talk about LLMs, we're talking about decoders, right? Like GPT family, which are generating, but one of the most important use cases for LLMs are encoding, like embedding generating LLMs, because search systems like RAG now, everyone talks about them, question answering system, but there are many other type recommendations. Like encoding generation is one of fundamental tasks, which is important for many practical NLP use cases, and LLM generation of like embeddings is one of the core tasks, and of course you want to evaluate your quality of and this kind of high level, like what I discussed, there are two kind of typically families of LLMs: generative models, like encoding models, and there are some intersections. There are some frameworks also how to convert generative to encoding. There is some kind of work to join them, but overall you have these two different families. And good example how evaluate encoding is there is a massive text embedding benchmark. It's a really good example because I understand encoding are different, used for very different tasks, right? So they have co-embedding tasks like by text mining, classification, pair classification, semantic text similarity. They're not completely comprehensive, but they cover quite a lot. And what you see from there, what you can learn also from this evaluation, you see like different models are winners for different tasks. And the same most probably will be in your practical cases. You want to design LLM, which will drive many different tasks in your company. And it's not necessarily one model will be the best for all of them. So certainly you need some variety of performance. You need certain complexity of having different models. And this evaluation leaderboards of MTAP shows it quite well, so different models do well. Even if tasks quite similar, they're all embedding, right? It's not like very different tasks, but nevertheless, different models give different different performance for different tasks. Like after you evaluate, like there are what I've noticed, academic community likes to use traditional information retrieval methods to evaluate, like recall at K, precision at K. And like from my experience, currently, if you measure, like if you build a question answering system on DAG, right, and you want to evaluate quality, people tend to use these old methods, like they're 30 years old, but they don't, like they were built when people built first generation of web, how customers look into results. People don't look results that same way. So it's important when you work on your evaluation methods to create metrics which represents your customers. Not kind of take as a like axiom, let's use this, you like, there are a lot of things to change. So in evaluation, everything should be questioned. Another important case, like what shows LLM evaluation, one is NLP accuracy, but also LLM embedding tasks they typically use like in search, right? You can have 1 million queries per second. You have 50 milliseconds for embedding generation. So those LLMs will be very heavily loaded. Of course, there are caching, many other techniques, but still, right? So evaluation of LLM and sense of software performance, cost, latency through output are also important for this sort of tasks. Again, it's important, right? One is metric, what you have, and then you have data sets on which you measure your LLM, sorry. And it's really important also not only design metrics, which represents your interest, but also to have data sets which represent your customers, represents your documents, so not to copy like just from MTAP data sets they have available, but to design it for your system. And there are many tasks in traditional evaluation, like rater disagreement. I've noticed academic community frequently kind of ignores them, but they're very important when you design systems for real customers. Again, it's important, like this is a good embedding, a good showcase, such that you measure embeddings to tune your models, to fine tune your models, to improve them. But customers are not directly exposed to embeddings, right? They do other search or question answering or recommendation systems. And it's also important as you create evaluation for LLM, not only to look into low-level language, like embedding level task, but also whole system performance. Like if you deploy a new model, what percentage in conversion of your recommendation engine, how much revenue per customer does it generate more, revenue per whatever, per month for your company. And to design such systems is another very important part of LLM evaluation. Like everyone talks about hallucinations, and there are a lot of almost every LLM system is exposed to them, and how to evaluate them, right? How to measure and evaluate them. There are several good works which are very practical. One is very clear, like if you look into a lot of research about hallucinations, there are very different types of hallucination, right? Like in this paper, they investigate 3 tasks: question answering, knowledge grounded dialogue, and summarization. And each of them actually produce quite different type of hallucination system produced for them. And they do a lot of deep analysis, what type of hallucination for them. What's important about this, like not just benchmark, but because, like if you want to measure something, you want to understand what to measure. And once you have deep understanding, like for example, factuality versus fastness, very different metrics, then you can design different evaluation system to measure those metrics. So this is quite good, one of like understanding of hallucination, but also evaluation them. There is a really good paper from Google, from DeepMind recently, and it's also very practical, implementable, such that you there are several ways how to detect hallucinations, and you can measure them. Basically, you get answer from your system, right? In that case, you use the LLM. Then you break answer into atomic facts, and LLM is very good in that. So if you want to create NLP layer which breaks your generated text into atomic facts, you can use LLM. And then you use external verifier. In that case, Google search, you can verify versus your system is all facts are done or grounded or not. Another pretty good evaluation system. And there is recently published another leaderboard for hallucinations, and kind of giving, they also consider like faithfulness. Basically, if you have like text and then you produce text out of this, like summary or like question answering, is this text related to this one or not? And factuality is like more like when you ask LLM a whole answer and like whole question, LLM replies with this internal knowledge. Those 2 different type of hallucinations, and how to produce them, how they're exposed to different tasks. You can design evaluation for your use cases. Quite good description. Code generating LLMs. It's like very close to GitHub Copilot, right? What they do. How to evaluate quality of the code. And what I like about this problem, right? It's very different problem from the text, because evaluation methods are very different. If you looked into papers about code generating large language models like before human eval, right? They were typically doing syntactic evaluations. They were trying to understand whole code. And the problem, it does not work well. You're trying to compare code versus some human written and compare others to chunks of code are the same. Good innovation from human eval. It was like, I think in 2021, they designed this. They designed if you want your system generates code. Do you want to check the quality of this? You design unit test, and then you checked if you produce code actually pass unit test. And they, of course, there are multiple versions. If how many of them pass, right? There are different things how to measure them, and it was very significant improvement. There is code glue, another benchmark, which good practice. And I believe this method is also good because, as you know, now LLMs will there are agent frameworks, right? When you expect LLM to produce a set of actions for agents, how are you going to verify are those actions are correct and achieve the goal. And the same framework, of course, it's not exactly the same unit testing framework and so on, but the same verification, I believe, is really useful to create such evaluation sets. There is a good paper from Microsoft recently when they evaluate Copilot. And like for me, it's close because I was designing other Copilot system, not for coding, but for business activities, and how you're going to evaluate LLM Copilot. So like agent which works with human to achieve certain tasks. And what I like in their approach, they very clearly define, like you can imagine Copilot do tons of different things. Let's clearly define what highest priority things, right? And they do very well it for coding Copilot. And they also very clearly define metrics and very clear how these metrics measure these tasks. This is pretty good kind of example how to design good Copilot evaluation system, which I found very usable, even not for coding Copilots, but for business-oriented Copilots, quite useful. There is a lot of now talk about like pairwise comparisons about arenas, and there are many of them on Hugging Face, there are many others. And in others, like evaluation, you don't give precise score to the particular model, but you compare model versus model, right? There are different ways how you do this. And arenas is very old used method of statistical evaluation and has its own like strong and weak points as evaluation methods. Just examples, you have chatbot from LLMs, you have negotiation arena. There is a good paper from Kahir when they talk about arenas as a whole method, how is it robust, how is it reliable as an evaluation method. They're useful, like now you have all these big arenas when you compare big models against each other, like Kahir versus Anthropic versus OpenAI. But they're also very useful for internal development. When you develop new versions of the model to understand, is this new model better than old one? And what's good about arenas, they let you to do a deep drill down, not just to give, oh, this model has 70, this 68, what does it mean, right? But you will understand through arena evaluation by deep details how these models are different, why one is stronger, why another is weaker, and what areas, how they can be used. So also arenas are much more powerful for incremental, like when like point-wise evaluation will not notice. Arenas very powerful in like when you do pairwise comparison, you will know like you have much more sensitive metrics comparing to point-wise metrics. So like again, it's like very strong, like not only for big model evaluation, like different families of models, but also different version of the same model. And key cloud providers like Google Vertex start supporting like them recently. You have in Google Vertex after side by side, they call it side by side, but really it's arena evaluation. In context learning is another big important task for LLMs, and there are like it's one of the first tasks which community started developing for logical LLMs. And those are really good practices which are used in many tasks, such that you can design similar tasks on your own, right? So like I will a little bit later. So like for example, Pika, right, is set to measure physical task. But I think it's more important to learn from this design of evaluation. You have a query, you have a set of answers, and then you ask, like you measure which answer is the best one. And it represents, they have questions for physics, but of course it can be applied to any physical domain. So if you design like a system such that will assist users on e-commerce shopping site to answer their questions, you're like, I would like to use, I want to buy like a camera for astrophysics. What is important for me, right? So many different domains question answering. You can use the same design to like principles design your evaluation set. And like Banda is kind of more low level, it predicts next talking, but also good to understand how good your LLM in deep comprehension and in the domain. Ethical AI evaluation, a very hard task, but I know everyone comes to this, like many companies talk to me, and there is not like comprehensive benchmark, but like everyone is concerned. Like remember, there are like several scandals when big company released chatbot. It was with Microsoft, it was with Google, it was with other companies, and then someone discard other finds toxicity or something else, right? Even recently, I think someone was writing about Facebook image generator. It was just today or something. So what about ethical AI evaluation? There are different evaluation methods, right? So like there are like toxicity, racism. They're actually pretty easy to detect. LLMs are good as classifiers for those tasks, but there are much more deeper, like beliefs, deceptive behavior, and there are several good papers, and there are actually several benchmarks you can find in my GitHub repository, benchmarks for measuring those behaviors. Another really important, I see everyone concerned about this. Another big area of evaluation is like, you're not necessary to use humans because humans, again, it's expensive, it's slow, right? You use another LLM to judge certain answers for LLMs. It does not work for all tasks, but it works very well for some tasks, such that LLMs very well aligned with humans. Again, it's important to measure as you design such tasks, but it works quite well. There was also recently good paper LLM as a jury. Instead of one judge, use multiple LLMs, and it works quite well. It takes a lot of manual work, right? As you create LLM as a judge, how to create template, which will measure your task, what is required by you. But as you do this, actually it works quite well. Of course, assuming like LLM will work for your task, it's always important to measure. Again, LLM as a judge may agree with human grading particular task, but it requires a lot of work on designing and tuning prompt templates, right? Of course, like, you know, like big LLMs as GPT-4 found to be working really well for many tasks, but they're very expensive and also quite slow, and you have to go to external API, right? The question, can you use small API like on your cloud, such which will be much cheaper, and you can run this like also fast and so on. So in each case, it requires some work. And sometimes, yes, for simple tasks, small LLMs can be used. Sometimes you need really big power. And evaluation of RAG systems. Everyone talks now about retrieval augmented generation. There are several other paradigms how to do LLM as a question answering, right? And there are several good metrics how to measure RAG. And typically, it really depends on your system. Like, for example, for medical question answering, you need very important to be authority of the answer, right? A novelty. For commercial shopping sites will be something different. So it's important to design metrics for your case. Typically you have answer, you want to compare it with graded answer, right? And there are like old metrics like Blue, Rouge. They don't work really well. There are like much more better developed, like BERT and BART based metrics for similarity. And kind of coming back, like there are several metrics which are popular across multiple evaluation frameworks now. I will explain their meaning. Faithfulness, answer relevance, context precision, and context recall. And there is actually a very good framework, Ragas, which is available as open source. Again, don't take it as a whole. You have to tune for your case. But it's like as open source, it's quite easy, well designed to tune because they just provide several metrics you need to design for your cases. And what they measure, right? So basically, as a RAG framework is based on you retrieve results for your query and then you generate results, right? So you have like multiple metrics, like faithfulness is how your answer is correct to respect to context. So you retrieved context, your LLM generates answer. Is the answer is exactly from context or did you edit facts? So this is faithfulness. Context precision, how question is really relevant to context. Answer relevance is answer is really answer to the question or not. And context recall, you can like it's only one way you need human rating because to measure all other three, you can do it with LLM. You basically break your retrieved text or answer into atomic facts and compare to each other. The only one you need to hear to like, did you get all recall, did all human recall, or did you get all context or not? And where you measure ground truth, you use some human created answers. This is how RAGs work. And then you can define on top of this many other metrics, which are more for your use case. Kind of more like I'm short in time. I will not be going deeply. The same definitions, what we use there. And this is how they computed. Again, notice that RAGs, it's kind of, again, from academic community, but again, from my experience developing multiple RAG-based systems, you need to define your metrics because they will be like your metrics will be very different based on business domain, what your system and what are requirements of your customers. And it's important to define it there. And some of them will be only you can do with LLM as a judge. Some of them you will need human created answers. And it's important to design your metrics. Another system, it was from Databricks, they kind of similar principles to RAGs. Like short of time, I will not go deeply into details, but basically they measure the same, like 1 second. They measure the same faithfulness, answer relevance, context relevance, but they basically use different methods. They don't break into chunks, they train LLMs, other LLMs as graders, so they do fine-tune LLMs as graders, and it helps them to achieve more higher robustness of results. And also you need smaller sets. They develop a statistical techniques such that you need only 150 human ratings in their case to do this. So there are a lot of quite nice work there from statistical point of view. And again, really important in your case, customize this metrics. And there are many other examples like how, like for example, this, I really like, it was article in Nature. They create LLM, which is for healthcare as a like copilot, and how well like they measure customer experience. It's very interesting way how you can apply the same techniques in your case. Evaluation harnesses, like how to build this, like what open source you can do, right? Because it's very involved tasks. There are many different things how you want to build evaluation. It's very non-trivial tasks. And you build from scratch is hard, easy to use, some good open source already available. There are several systems, like for me, it's preferable, like from my, I have best experience with Evaluator AI. This system is used like perhaps now, okay, 60% of academic papers, if you go to a big conference using this, like a Hugging Face, leaderboard, like evaluation boards were used on this, is most popular. And it's very powerful because it's integrated with a lot of like VLLM, many other serving frameworks it's integrated with. It's evaluated with many accelerators. So like Evaluator AI is the best, like there are several other systems, but from my experience, Evaluator AI is kind of the best one. Let me go fast and just few last slides. Another really important part is, of course, because LLM is frequently used in production, right? You know, like so NLP metrics, accuracy is just part of this. Others, will it support your load? And it can be serving system, it can be streaming, it can be batch processing. And what I found typically okay about GPU utilization, like GPU expensive, very important to understand how your system is kind of not overall, not how to say, like, don't you have to manage it? Because I've noticed some people now tend to give big cloud. It becomes very expensive. So kind of how is GPU utilized inside your system? How do you automatically allocate and so on? Total latency. There are several different like a latency per token. Latency to the first token depends on use case. Each of them different. And of course, operational metrics. You care like model is overloaded. Sometimes you get even with ChatGPT, you ask something more, you don't get answer. User engagement metrics important as whole to whole, like end to end. Just the last slides. And of course, quality of response. Yes, thank you very much.
And we can. You're going to be staying around, so we can have a question after.
Okay. Thank you very much.
Thank you. Right. I think we're going to move on to the second speaker. We have Yujian. He's going to be talking about the customizing vector database.
Recording in progress.
All right. Great. How's everybody doing? I see some people walking out. I promise my talk is not going to be that boring. All right, first, let's get a show of hands. Who's seen me before? A lot of you who've seen me before. Who's seen me give this talk before? Only two. Great. Okay, so you guys are going to be in for a new talk. Actually, it's going to be a very similar talk. It's just going to be slightly different. So who knows what a vector database is? All right, who knows what RAG is? Oh yeah, you guys just heard us talk about that, didn't you? Yeah. All right, cool. So my name is Yujian. We're going to be talking about Milvus. Who's heard of Milvus? All right. Great. So there's a lot of people who already have some background knowledge. For those of you who don't know me, I'm going to give you this time to scan this QR code here. This QR code is going to take you to my LinkedIn where you can find me and ask me any follow-up questions or keep up with anything else around generative AI. I give a lot of talks. I do a lot of events. I do a lot of workshops. So if you're interested in any of those things, feel free to scan that QR code, find me on LinkedIn. How did I get into this? How did I get into working on these things? So I started working in software way back in 2013. And then I went to college and I studied some machine learning, published some papers on machine learning. mainly focused on CV and big data before I transferred to, I went to Amazon afterwards to go work on machine learning. I worked on the AutoML platform there. And then I got into startups, and that's when I got into natural language processing. And that led me into, very naturally, generative AI and retrieval augmented generation. And so in this case, in this talk, we're going to talk about why you would use a vector database, how they work, what are some example use cases, and then at the very end, we're going to talk about the most interesting thing for most technical people, which is the architecture. I can blaze through some of the use cases and stuff, and we can get to the architecture faster. How many of you guys are software engineers? Okay, how many of you guys want me to kind of skip through things quickly and get to the architecture? Okay, so not a wide majority, but some of you do. So I will try to get to the architecture quickly, and we'll talk about some interesting things. So the first section is always motivation, right? Why do we even care? Why should you use vector databases? So vector databases allow you to compare data that you couldn't compare before. This is the main premise behind vector databases. And the reason why these things exist is because unstructured data is everywhere. So, things that are not in table formats is basically what unstructured data is. Anything that's not in table format is what we consider unstructured data. And at some point, the IDC estimated that there would be 80% of the world's data is in unstructured format. So I'm talking about like videos, audio, text, things like that. And basically, unstructured data can only be quantitatively compared if you can turn it into some sort of numbers, right? So text itself is not really something that you can compare quantitatively. But once you get into number format, that's something that you can start comparing. And so the way that this works is that you turn this unstructured text into vectors using some sort of machine learning model. So who knows about neural networks? Who knows what a neural network is? Basics of a neural network, most people. Okay, so in a neural network, what happens is you take your input data, you transform it into some sort of number series, whether that can be tokens for text or pixels or whatever, for images or things like that. You take that, you turn it into some sort of numerical input, you pass it through the model, and the model gives you some sort of prediction, some sort of regression, some sort of classification, something like that, okay? Now, during that process, the model starts to develop something like an understanding of the data. And so we call that a semantic representation. And at the second to last layer of the model, you get the model's full semantic representation of that data. And so the way that vectors are collected, the vector embeddings, are the output from the second to last layer of the machine learning model. And that's because that output of the second to last layer has all of the semantic representation of that data. And then once you have that, you put that into a vector database like Milvus or Zilliz, and you can start compare it in a quantitative manner. All right, so let's do some exercises here. Let's do some exercises and let's be a vector database, okay? So actually, we're going to do the opposite of what vector databases do. So I've got some semantically similar data on the screen here. So the sentences I've got up are Apple made profits of $97 billion in 2023. I like to eat apple pie for profit in 2023 and also 2024, if anyone wants to pay me to eat apple pie. Apple's bottom line increased by record numbers in 2023. So these are your three sentences, and what we're going to do here is we're going to compare these sentences semantically. So who thinks that the first and the second sentence are the most similar? Nobody. Okay. I see some people pretending to think. Okay, what about the second and the third? Nobody. Okay, what about the first and the third? If you think the first and the third sentences are the most similar, raise your hand. I see some people not paying attention. All right, so yeah, exactly. This is why I'm asking all the obvious questions here. So the first and the third sentences are the most semantically similar, but if we were to backtrack just a few years and we were to think about how search was done just a few years ago, keyword search is how you would search text. And you can see that if you search for Apple profits 2023, you would get back the first two sentences. And so semantic search allows you to do this new kind of search that you were unable to do prior to vectors and vector embeddings and vector databases, okay? And it's not just text, it's also images. So those of you who've seen me before know that Taylor Swift is one of my favorite musicians. So we're gonna do another reverse test where we're gonna see which one of these is not Taylor Swift, okay? So first one, raise your hand if you think the first one is not Taylor Swift. Everyone thinks the first one is Taylor Swift. All right, what about the second one? Raise your hand if you think the second one is not Taylor Swift. All right, a lot of you guys don't think the second one's Taylor Swift. What about the third one? A lot of people, who thinks the third one isn't Taylor Swift? All right, don't be shy. What about the fourth one? Who thinks the fourth one is not Taylor Swift? A couple of you, okay. It's all four. All four of them are Taylor Swift, huh? Well, you, sir, would be wrong. The second one is the one that is not Taylor Swift. So most of you who raised your hand for the second one, you're right. So what I want to demonstrate to you with these images is that as humans, we have this kind of inherent capacity to recognize which of these images are similar. But machines don't have this knowledge. Machines don't have an inherent way to recognize that, or they might, but we haven't found it yet anyway. And so this is another thing the vector database will allow you to do. By taking these images and finding the semantic similarities between these images, by quantifying these images, you can compare them and find which ones are most similar. All right, so basic idea behind all of this is that you're using math to quantify relationships between entities or objects, okay? So let's move on to how vector databases work. How do they actually do this kind of comparison? So vector similarity is just a mathematical measure of how close two vectors are. Raise your hand if you know what a vector is. Great, okay. So we're gonna cover a very, very famous vector representation example. And this is the king, queen, woman, man example, okay? So I want to point out some things to you that are important for this slide, but you know, I also want to point out that this is a toy example and that you will never see two-dimensional vectors in production, and you will probably never see anyone use Manhattan distance in production. Okay, so one thing I want to point out here is that the words queen and woman and king and man have the same value on the first dimension. But all that tells us is that these words mean the same thing along that dimension. This is a relative measure. It doesn't tell us what that dimension means. So it doesn't mean the first dimension is gender or sex or whatever. It just means that these words have the same meaning along that first dimension. Okay, so now we can move on to the math. So queen is 0.3, 0.9, and we're subtracting woman, which is 0.3, 0.4, and we'll get a value of 0, 0.5. Does anyone want to venture a guess at what word this value might represent? Any brave souls in the audience tonight? No brave souls in the audience tonight, all cowards. Yes, who said royal? Ah, good job. All right. That's what I think it would mean, but we don't actually know because the authors of this paper didn't provide the actual word. And then you add the word man, which is 0.5, 0.2, and you get the word king, which is 0.5, 0.7. So actually you get 0.5, 0.7, which relates to the word king. So all you really need to take away from this, if you didn't follow me saying all this like add minus stuff, is math on words or other things. Math on things that aren't originally numbers, that's what vectors allow you to do. So beyond that, there's two things we need to look at. One is similarity metrics and one is vector indexes. So first we're going to look at similarity metrics. So earlier I mentioned this type of distance called Manhattan distance, which is where you're just subtracting and adding the values directly. But in reality, nobody really uses that. What we use in vector search is more similar to things that you probably learned in geometry. So who here has taken geometry class? Great, so you guys remember hypotenuses, right? Last time I was up here, I forgot the word hypotenuse for like a good 30 seconds. But this time I've remembered, so you guys remember hypotenuses, right? A squared plus b squared. So this is basically the same thing, right? This is the distance in space between 2 points, Euclidean distance. That's all you need to know. Just look at the equation, look at how complex it is, and just have an idea of this, okay? That's all you need to know. This measures distance in space. Next, we've got inner product. Inner product measures the projection of one vector onto another. Who here is taking calculus 1? Trigonometry, yes. You guys remember inner product, right? No? Yes, no, okay. Some people have traumatic memory loss. So this measures the projection of a vector onto another, which involves both the angle and the actual magnitude in difference in space. So that's what this is. And you can see from the formula, this is a very simple formula, AI times BI. It's really nice. Now we move on to the next one, cosine similarity. So if you go online and you look at vector databases, you're going to see a lot of people using cosine similarity. And the reason they're using cosine similarity is because a lot of NLP papers use cosine similarity. And the reason a lot of NLP papers use cosine similarity is because early researchers liked cosine similarity and trained models that were specifically designed to use cosine similarity. But that's no longer the case. So don't take everything you read online for fact. And cosine similarity, as you can see from the formula, is the most computationally expensive of all three and is actually my least favorite. And there was a paper out recently that showed that cosine similarity does not actually measure similarity, so I feel very vindicated. But as you can see, cosine similarity would measure the distance and the difference in orientation, the angle difference between two different vectors, okay? So we've just covered 3 ways that you can measure vectors. You can measure the spatial distance, the magnitude. You can measure the orientation distance, the angle, cosine similarity. You can measure inner product, which is a projection of one vector onto the other and measures both. Or when you are using normalized vectors, that is when you are using vectors with a magnitude of 1, you can see here that we have normalized A and B in the cosine formula, then your cosine similarity is actually equivalent to inner product. So in all cases, inner product is a better measure of similarity than cosine. That is my personal opinion. That is not backed by Zilliz. That is my personal opinion. All right, indexes organize the ways that we access our data. So indexes, who here has worked with SQL? Okay, so you guys are all familiar with the word index. This is somewhat similar. This is the way that we access the data, okay? So we're gonna go over a few different vector indexes. So the first vector index that we're gonna look at is called inverted file index, which is abbreviated to IVF. Doesn't really make a lot of sense to me, but that's just how it's been abbreviated. So the reason why it's called an inverted file index is because in a regular index, let's say you have a list and you say list 0, that gives you the first entry in that list. However, in IVF, it is the opposite way around. You give me the entry to the list and I will give you where it is placed. So that's what inverted file index is. And the way that it's created is essentially you run a k-means algorithm and you find a bunch of centroids. And then you keep track of the centroids, and at search time, you search through a specific number of centroids, and then you search through the top 10 closest centroids, and then you take those and you pull all the vectors from those centroids that are within those regions, and then you search those regions. Okay, so that would be what we call IVF flat, and later on you'll understand what flat means. So that's inverted file index. It's very intuitive. It's basically saying we're going to just k-means, get a bunch of centroids, and then search those centroids. Next, we have hierarchical navigable small worlds. Try saying that 10 times fast. No, don't actually try it out loud. Sorry, I do give a lot of interactive things, but this one is not one of them. So in this one, what you're doing is you're basically creating a graph of the vectors, okay? And let's see, how should I explain this? So when you create this graph, at insertion time to this graph, when it's being created, each vector, you're inserting each vector into the graph. And each time you insert a vector into the graph, you're going to compute a uniform random variable. And you're going to use some sort of exploratory factor to determine which layer that goes into the graph. So every single vector goes into layer 0. But depending on the value of the uniform random variable, it may go all the way up into layer 1, 2, 3, 4, 5. So for example, if my cutoff was 0.9, then all vectors go into layer 0. Vectors between 0.9 and 0.1 will go into layer 1. Vectors between 0.99 and 1 will go into layer 2, as well as layer 1. And vectors in between 0.999 and 1 will go into layer 3, and so on and so on and so on. So at search time, you start at the topmost layer that is created from this kind of process, And then you just say, hey, what's the closest vector in this top layer? Okay, we found it, and now we go down to the next layer. In the next layer, you can look at the closest points to that vector, can see which one of those is the closest points to your actual vector, and then you get the closest one of those, and you go down, you go down, you go down, all the way until you get to layer 0. So you can kind of imagine you're storing a lot more data with HNSW than you would be storing with IVF. So IVF, you're just kind of storing the centroids and the vectors. With HNSW, you're storing the vectors and their relationships, the graph. Okay, so HNSW is a very memory-intensive index. However, you can also imagine, because all of these vector distances are computed already and they're held in memory, it's very fast. And not only is it very fast, but because you're also using a graph and you're able to find all of the closest vectors in this graph, it's also very, very accurate. So HNSW is very memory intensive, but it's very fast and it's very accurate. Okay, so next we're going to go into things that would be, I would say, these are indexing methods, but these can also be tacked on to the other indexing methods, okay? So this one is SQ, or scalar quantization. And you can kind of just think of this as bucketing, right? So, you know, you guys are familiar with like real numbers and integers, right? Raise your hand if you know what I'm talking about when I say that. Great, okay, cool. So if you just take the real numbers and you bucket them into the integers, you can kind of think of that as scalar quantization. You've taken one set of infinity and put it into a smaller set of infinity. And so an idea here would be maybe you have -10 to 10, and then with -10 to 10, you now can put that together, and now you have, instead of 0.4568, you have 1 or 0, something like that. Next, we have product quantization. So product quantization is scalar quantization, but done again. So you can kind of think of this as two-dimensional, doubly dimensional quantization. It compresses things a lot more than scalar quantization. In fact, it compresses them at a product level. So if you were to compress them 8 times in scalar, you compress them 64 times with product. As you can think about this, a lot more compression, less memory, less accurate. It's kind of just how that works. So the indexes are IVF, HNSW, flat, which is just brute force, and then SQ and PQ. And you can combine IVF and SQ and IVF and PQ, or HNSW and SQ and HNSW and PQ. And you can kind of get the best of both worlds, doing a quantization as well as an accurate index. So for example, you might take HNSW and combine it with scalar quantization if you want something that is going to be very accurate, very fast, but you want to make sure that you're not taking up 3 times the memory that you need. All right, so basically vector databases provide you different ways to store the data, to index the data, to compare the data, things like that. So what are some use cases? First, we'll take a quick look at vector data. So the first 2 entries are all you need to think about here. So your ID and your embedding are required for vector data. So that's your ID is how you access the data, and the embedding is the actual data itself. The rest of it is called metadata. That's what you use when you need to compare the data, when you need to filter the data, when you need to use the data after retrieval. So for example, when you're doing RAG, you have to store the text and the metadata. And there's actually many advanced methods for that. You can come to one of my other talks and I'll talk more about that. Oh, and RAG, yes, this is the most popular current use of vector databases. Who here, like you guys are all familiar with RAG though, right? Like you guys saw like the last talk about RAG. Okay, great. So I'm not gonna talk about this. Okay, so common AI use cases. These are basically ways that you can use vector databases: image search, image similarity, video similarity, audio similarity, text similarity. Notice the trend here. Similarity search is the main use case for vector databases. So in any case where you have similarity search, this is something that's useful to you. Okay, QR code time. So scan this QR code if you want to get some RAG cookbooks. I've got some notebooks in here that'll take you to examples of how you can build retrieval augmented generation applications. And I see some phones up, so I'm gonna just pause here and kind of like talk into the microphone and say things that don't really mean anything. All right, phones are still up, so I'm gonna mumble a little bit more. Okay, it looks like everybody's got these. So next, AI agents. Who's heard of AI agents? Yes, great. This is the next big LLM hype. This is the next big suite of tools that you'll need to know for generative AI. So I've got about 10 notebooks here that you can use to build AI agents. Not all of them use vector databases. Only the retrieval augmented generation agents use vector databases. But something that you probably want to get an example of how to use. So AI agents are basically just LLMs that can use tools. Some people have described them as LLM for loops or recursive LLMs. Either way, just tool use. All right, before we get into the architecture, Josh, how am I doing on time?
We got 3 minutes.
3 minutes. All right, cool. So we're going to try to blaze through this as fast as I can. So this is the architecture of a vector database. Actually, this is specifically an architecture of Milvus. So what's important to note here? Okay, Milvus is a distributed vector database. Who's familiar with distributed systems? Who took distributed systems? Yes, all right, okay. So, and then you'll understand that some of the problems with distributed systems include consistency at scale, such as write consistency at scale, read consistency at scale, being able to have enforce read over write, being able to write from multiple sources into one source of truth, things like that, okay? You probably also have an understanding of stateless. So you'll see this node thing in the second layer from the bottom. You'll see a bunch of nodes. These are stateless nodes that are all coordinated by what is at the top layer, the coordinator service, which is a stateful coordinator service that keeps track of all the state, knows what's going on in the nodes. There are 3 different types of nodes available in Milvus, and these nodes are the query node, which does the searching, the data node, which does the data ingestion, and the index node, which does the creation of indexes, okay? And the reason why you have 3 separate nodes that do 3 completely separate things is because these 3 things are the 3 main concerns you have when it comes to search, and these 3 things never scale at the same time. You will never have, okay, maybe not never. You will almost never have a use case where you are inserting millions of entries at the same time that you're querying millions of entries at the same time that you are creating millions of indexes, okay? This is just not something that typically happens in any known workflow. And so you want to have a way to scale all of these things separately. Beyond that, you also want something that has a decoupled read and write system. And this is incredibly important when it comes to distributed systems, because you are going to have to write from multiple sources into one single source, which needs to be read back into multiple sources. And so the way that Milvus handles this is using a message store, which we call a write-ahead log. And what this does is it essentially takes your messages and it publishes them into it writes your messages into a stream, and that stream then publishes your data, and then that data is then subscribed to or read from by the data and the query nodes to get data into Milvus. So it's a loosely coupled pub-sub system. Who's familiar with Kafka? Okay, so you can think of the different write shards as basically Kafka topics. Okay, so that's how we enforce write consistency. And the way that you can enforce read after write is essentially what we call timestamps. So each time your data gets written into the pub subsystem, there will be a timestamp assigned to that data, and that is how we can tell whether or not when your data was written, and so that's how you can tell when your data will be read back. So that's how we handle the multiple read sources from multiple write sources, okay? The last thing that is of interest that you can't really see from the diagram is the way that data is segmented. So indexes have to be created over segments of data. And this is really important if you have data that's going to change over time. If you're just going to put your data in once, you can index it once, doesn't matter, and then you can read from that. But what happens if you have 100 gigabytes that you want to index, and then the next day you've got another 100 gigabytes? Well, it's incredibly inefficient to read 100 gigabytes at once, so you want to reindex that, and maybe you want to find a way to reindex that and store it and do it automatically and have your search over that be efficient and effective. So what Milvus does is it actually takes your input and it segments up your input into X gigabytes, 2 gigabytes, 512 megabytes, whatever, and it builds an index over that. And then that's why we have all the proxies and the load balancers. Another advantage of distributed systems is you'll be able to then search all of those in parallel, aggregate them, coalesce them, return them into the proxies, which will then return them to you through the SDK. So that's a quick overview of Mills' architecture. And I think that's it. Cool.
Let's take maybe one or two questions. Anybody have
yep.
a question for Yujian?
Oh yeah, let me put my slides back up. I'll let you handle the questions, Josh. Great. I'm going to take this all the way back to the most important QR code, which is the QR code of me.
Great job.
Thank you. All right, you can shout.
Film right here. That's good.
Yes, I can hear you.
Behind the phone currently.
Okay.
And something super frustrating for me is I can't delete vectors on metadata search.
Okay.
Is that something we can notice?
Yes, you can delete vectors in Novus.
I mean, any reason to store the vector IDs of all the vectors on my end?
If you want to delete by vector ID, yes, you would need to do that. If you want to delete on vector search, you can use an expression filter. So Milvus supports metadata filtering through expressions. And then you can get all those vectors back. And I think you can get the IDs for those vectors back and then do a mass delete if you need to. Yeah. Yeah.
All right, one more question.
Hey, good to see you again. Ah, great question. I hate cosine similarity, so this is I planted this guy in the audience. So cosine similarity is, let's go back and look at this, right? Cosine similarity is the dot product divided by the the magnitude of the vectors. So this is fine for measuring like orientation distance if you only have normalized vectors. But the reality of the situation is not all vectors are normalized, and LLMs don't always normalize their vectors. And so if you want to be able to measure not just the orientational distance, but also the magnitude in space, you're going to need a better similarity metric. And that better similarity metric is inner product, which is my favorite similarity metric. Although the Milvus examples use a lot of L2, which is also great. This measures your distance in space, also really good for non-normalized vectors. But as you can see, inner product is a less computationally expensive similarity measure.
So you're basically saying that with the cosine similarity, you're just basically dot product over. You're basically removing the denominator because the dot product is essentially.
So I mean, yes. Yeah. So like the other thing is like vector embedding models, which are trained on cosine similarity, exist. And those are actually the original NLP models that were used for similarity search were trained to do cosine similarity, but that is no longer the case. And so it's like, if you have a model that's trained on cosine similarity, you should go ahead and use it. I would still use IP because it's cheaper and it does the same thing. But if you don't have a vector similarity metric that's a vector embedding model that's trained on cosine similarity, then you should use another measure of similarity. Great.
All right, you're going to be here after. So let's get ready for the last speaker. Come on up. And we have Pranav, and he's going to be talking about the AI. Awesome.
And then you. Screen here. Okay. So great. Let's. Okay. So yeah, let's talk. It will be quick, and I'll do a quick intro about deep learning and how it's used for audio processing. This field is evolving and lots of new developments happening. And the reason I chose this topic was that as developers and data scientists, typically we don't deal with speech data, but maybe in the coming few years that might change. So it's good to like have some idea about speech processing as well, alongside image processing and text processing. So I'll dive a bit into the history and how things used to look like, because I'm like, for me also it's very new and I'm also still learning about the field. So let me do a quick like glimpse of how it used to look like. So this is
Either the vibration of the vocal cord. There are no phonographs, anything of that sort. Only a telephone line. Let's see how you put expression into a
yeah,
sentence.
this is very interesting. 1939.
With no expression. Now say up an answer to these questions. Who saw you? Whom did she see? Did she see or hear you?
Okay. Yeah. in text you have there is an echo when I. Why does it repeat the word?
It was a little hard to hear.
No, but maybe I need to. Okay. Yeah, yeah. Okay. So yeah, so NVIDIA seems to be topping the charts now, and it has some very interesting research coming out, and they also have this monthly office hours where they let voice researchers you working with voice, they let them collaborate. So that's something you might want to check out. So if there is something that you want to take away from this entire presentation is like, yeah, check out NVIDIA for speech related AI developments. So what are some of the approaches that people use to model speech? The first one is contrastive modeling, and where you want to, so the layman version for contrastive modeling is that you have, so you create fake positive and negative samples, and then you want to maximize the distance between them. Like your model is basically learning how to maximize the distance between two things that are of very different types. And there are different ways to do it. I won't get into the details, but that's a layman version of contrastive learning. Then there are predictive approaches, right? BERT is, I mean, the best example. Like all these, even GPT, right? It's like predicting the next token. Then there are generative approaches where you are trying to model the P of X, right? Where X is your audio. So you want to be able to generate audio from scratch. And that is, so, uh, so some of the examples there are like these auto encoders and like some other such examples where you want to generate and model the entire like P of X, the audio itself, and rather than saying P of Y given X. In predictive, you are like P of Y given X because you know X and you just want to predict the best Y. But in generative cases, you model P of X, which is the actual X. That's the audio, not the text that will come out of the audio or the classification that will come out of the audio. It's the audio itself that you want to model. And so if you see like lots of models, right, just like text processing, image processing, but I feel the transfer learning boom that happened, like the ImageNet moment that happened for image, and then with transformers, it happened for text. That moment, I would say, probably again, it's my guess. I'm not on the cutting edge in the field, but it seems it sort of happened around 2021, 2022, with these wave to vec style, like especially wave to vec 2.0, like how they were able to just do this unsupervised pre-training on raw audio, hours and hours of raw audio, and then based on that, like in a few shot, do speech recognition, speech to text. And that's something very recent. Like if you, I mean, in like all these big advances with unsupervised learning, they happened for NLP in like 2016, 2017, that time. In images, I guess they happened even earlier. But for audio, it's still happening. So if you want to get into the field, this is the right time because lots of cool stuff to be done. And yeah, so I think I'll just pause here. And I have a demo as well, but I'm not sure. If we don't have the time, I won't go into the demo. But this is a Jupyter notebook uh, where I, yeah, like use some of the open source Hugging Face models and like fine tune them and generate some audio samples from these deep learning models and all that. So I'm not sure. Are there like, do we have 5 minutes or 10 minutes? Okay, yeah. So yeah, there is a very nice course from Hugging Face. I would really encourage if you want to get into this field. It's not, I think it's not that easy to see the screen. So how can we increase the contrast? See, maybe there is a. Yeah. Someone said something? Okay, okay. Yeah, yeah. So I'll try to stay in that half. That is the half that's more visible. So yeah, so you see the usual culprits. So right, I mean the usual suspects, right? The transformers package, then the datasets package. But you see these other changes that you do when you are working with audio. So you need to downsample the audio. You need to do certain things like probably some libraries calculating the spectrogram of the audio and so on. So that's why you need a few extra libraries. And then that's it, right? All of everything else seems very familiar. Like instead of having, if you were doing text processing, then you would have, I mean, some kind of tokenizer, but that tokenizer is called feature extractor in the case of audio. And so, Hugging Face has made it quite easy to work with audio and do all these niche processing tasks that would generally happen with like very or very different libraries. Like now Hugging Face lets you do all of that right here. And so now I load this data set, which is a data set of people calling like uh, companies and describing their problems. And it's like it has different languages, different dialects, and so on. So let me, yeah, I'll actually play a sample from this. And right, so I created a little Gradio demo to demonstrate this. And okay. So that's fine because I already did what I wanted to do. Yeah,
my electricity bill using my car. Can you please assist?
okay. So this is the Yep. So this is yeah, this is the audio and this is the waveform, and this is the classification, right? So there is a deep learning model that you load, and in 3 lines of code, it just like tells you what the category is. And here it's pay the bill, which is actually the ground truth, like which is true. That's what the person was asking about. And now let's go to like ASR, which is automatic speech recognition, speech to text. So, right, I mean, this is the text that we got from that audio that I just played. So I would like to play my electricity bill using my card. Can you please assist? So the model got the card part wrong, like this one error. And even the best deep learning systems, right? If you see that leaderboard, NVIDIA, like it was like this 4 or 5% word error rate. So still, I mean, there's room to grow in that space, like how to accurately transcribe speech to text. Now let's generate some rock music from the 90s. And so it's very funny, right? Like there is this text to audio model, and you just say what kind of music you want, and then it will, yeah, it will just play that for you. So I'll mute myself. So yeah, so right, I mean, it's not the best music, but still, it's nice that we can just give a prompt and generate audio. Then let's fine tune a music classifier. So here what we'll do is we have this data set that has a bunch of music of different genres, and we fine tune a model to classify the music, given a music, classify it into the right genre. And so it has lots of genres, and like this pop, and I won't play all of them, but there's pop music, there is metal, there is blues, there is rock. So all these genres are there, and you use this model. So let's skip to the, so right, you see this code, it's very small, like it's just like you were training any like text model, and you were fine tuning some text model. It's like the same, just that you have to get the audio into the right form. Like having clean data is actually not easy in when it comes to audio tasks. Now you see, like I have this those who are familiar with Hugging Face, they'll realize like all of this is so similar to text like NLP stuff, and that's exactly like what I do for a living. I do NLP, but for speech also now with Hugging Face's tools, it's very easy to do this training. And so you define the metrics, and then you have the trainer object, and yeah, you just trainer.train. That's it. And so I didn't finish the training process, but you can see the accuracy is going up, and that's how you can fine tune and work with audio data. And there are lots of open source models available now, and even Whisper, right? Like the cool thing is Whisper is also not that big. Like OpenAI Whisper is maybe a few billion parameters. That's it, if I'm not wrong, or maybe it's just 1 billion. So yeah, I think that's why like the models are not that big, although the like it requires a little more domain knowledge when compared to text processing and image processing, but still I feel it's a very exciting field to get into. And I'd love to hear what all you want to build or have been building with this speech modality. Yeah, thanks a lot.
All right, shall we take a couple questions?
Yeah.
Any questions for Pranav? Yes. Go ahead.
From my experience, it was very interesting for me of comparison of Whisper versus NVIDIA models, like because from my experience, I see more people using Whisper, and I think it just maybe more people has practice with this, how to fine tune, right? Because frequently you need to fine tune it for different domains because of special language, right? Like from your experience, is NVIDIA like kind of easy to use, like the same as with Whisper models? That's one. And so, like what your experience with NVIDIA models for fine tuning? And another, what model family would you recommend for text to speech, right? With commercial license, because there are several without commercial. What text to speech models would you recommend for commercial license, with commercial license?
Yeah, I'm also very new to this space, so I think I don't have a great answer right now because I've never really worked with speech data. I'm also like a hobbyist. I just like learned something about speech, and then I'm just sharing it with the community. But yeah, I think those are good questions. I don't know like what's typically used.
Did you try like NVIDIA models to fine tune them?
No, I haven't. No, I'm not. Like I mostly dealt with Hugging Face models. I didn't use. Yeah, but that's something. We should try.